Here, we'll examine how specific ecosystem processes change with primary and secondary succession. Successional changes occurring over decades to centuries explain much of the local variation among ecosystems. So if we think back to the example we had from Alaska that showed differences in burns and revegetation after the burns, and some of those burns, for example, led to deciduous forests, others mixed and dominated by spruce. Younger patches, more recently burned patches, hadn't necessarily developed a strong forest cover yet and were still very open. As we walk through this landscape, a lot of the variation that we see here has to do with differences since time of disturbance. Some of the areas may not necessarily have been disturbed. It might be the differences that we see in vegetation and the ecosystem parameters might not necessarily be due to differences in disturbance, but a lot of the variation that we see in a landscape like this has to do with patterns of fire and disturbances caused by fire. So when we think about the variation that we see on a landscape scale, some of that's going to be due to differences in topography or parent material, for example, or even human activities. But a lot of it is really time-sensitive disturbance, and with relatively minor disturbances, succession; with relatively major, severe disturbances, changes in ecosystem development. So differences in disturbance regimes, disturbances, succession, ecosystem development are factors that generate a lot of local variation in ecosystem processes. Primary succession occurs after severe disturbances that remove or bury most of the products of ecosystem processes. So in our case for Mount St. Helens, that was a case where revegetation was starting with soils that hadn't had any biotic inputs. And that was a pretty severe disturbance. And that led to really burial of most of the products of ecosystem processes, but others were removed due to erosion. When we think about primary succession, the initial state of the ecosystem, there tends to be very little nitrogen in that system because nitrogen is not rock derived, it's biotically derived. Water holding capacity also is often low since it's dependent on soil organic matter. The patterns shown here are the accumulation during succession of soil organic carbon and associated cation exchange capacity for mineral soils. And this is after deglaciation in Glacier Bay, Alaska. So what we have here on the x-axis is successional age, starting at 0 and going to 250 years. So this means 0 years, or in this case probably 10 to 15 years, after a glacier retreated, 100 years, 200 years after a glacier had retreated. And on the y-axis we have soil carbon, kilograms per meter squared. We can take a look at soil carbon development, and it increases more or less linearly for a while and then starts to level off. And then cation exchange capacity. And these are two of the changes that we see with successional age as soils develop. Soil carbon accumulates, and associated with that, cation exchange capacity. Now for both primary and secondary succession, the pattern of dispersal is really important. Especially in a primary successional system, nitrogen fixers facilitate later successional species. So if we take a look at the patterns of nitrogen, if there's no nitrogen fixers, they're going to be relatively low over time. The amount of nitrogen that comes into the system from atmospheric deposition might be retained and lead to a relatively small increase. But once nitrogen fixers move in, they can really increase the nitrogen content of the soils, and as a consequence, produce nitrogen that's then available for later successional species. This is figure 12.9, and it shows the interaction of life history traits, competition, facilitation, and herbivory in causing successional change after glacial retreat in Glacier Bay, Alaska. So these are, as we work across here, we're going across time or distance from the edge of the glacier. So we have the pioneer and then other different stages. The pioneer stage is dominated by light-seeded species. So these are the first species to disperse in to an area. And then Dryas is a shrub, but grows relatively quickly. Still, it's relatively short-statured. The alder stage, alder fixes nitrogen, and alders dominate this area in the intermediate term and really build up the soil organic matter and the nitrogen in the soils. As they do that, once nitrogen content's high enough, spruce is going to disperse in and then begin to dominate and shade out the alders. What this shows are some of the interactions among species and ecosystem processes that generate some of these patterns. Some of the patterns are due to simple dispersal and differences in dispersal rates, but some of those are associated with facilitative effects. For example, increasing nitrogen availability makes it more likely for spruce to move in, but there's also inhibitory effects and changes in herbivory that promote or retard different stages. Secondary succession, in contrast to primary succession, begins on soils that developed beneath vegetation. So when we take a look at primary succession, one of the things that changes over time is going to be the amount of nitrogen or soil organic matter in the soil. A lot of species are going to be inhibited or not necessarily promoted by low nitrogen availability, low soil organic matter. With low soil organic matter, it's going to be low cation exchange capacity and low water holding capacity too. So the rate of vegetation change and ecosystem change in primary succession is dependent on the rates of soil development. Secondary succession, for all intents and purposes, doesn't have to rely on species to build up soil organic matter, and so it can happen a lot faster compared to primary succession. So with secondary succession, we have soil organic matter already in place. But in addition, often with secondary succession, there's a seed bank. With primary succession, where you don't have soils, you're not going to have seeds that are in the soil, and you have to rely on dispersal into the site, which can be relatively slow. With secondary succession, there's often seeds that are in the soil that can germinate post-disturbance. In addition, in many systems, there's what's called a seedling bank. And a seedling bank often sits in the understory, and they're relatively small trees that are suppressed and don't grow up until you have a disturbance. Then these release and become the next stage of secondary succession. So it's even faster than starting from seeds. There are also patterns to water and energy exchange with succession. Disturbances that eliminate plant biomass increase runoff through a reduction in evapotranspiration. This has been shown in forestry systems relatively well. This is time on the x-axis, and just think of this as years, and on the y-axis is stream flow. In this case, it's stream flow deviation, which is how much more or less compared to a base year or an average. So in this system, this is for a North Carolina forest in the southeastern US. We have a calibration period where they're taking a look at the base stream flows, and then what happens after forest harvest. After forest harvest, stream flow increases greatly and then declines over time. And what's happening here is that over time, you go from a place that has a lot of leaf area with a lot of transpiration to one that doesn't have a lot of leaf area. Over time, leaf area develops, and as a consequence, you have a greater partitioning of water that goes to stream flow versus evapotranspiration. So that's what we're seeing here, is that all this water that used to be evaporated or transpired is now going into the streams. Along with changes in leaf area, for example, that have to do with evapotranspiration, we can have changes in albedo over time also. These are successional changes in albedo after a fire in Alaskan boreal forest. We showed before that post-disturbance, so after the fire, these systems are really black. There's not a lot of albedo there at all. And as a consequence, over time, as vegetation recovers, albedo is going to go up. Albedo increases during the herbaceous and deciduous forest phases of succession, so all those light green plants that we saw start to dominate, and the albedo is really high. Then it goes down over time as spruce moves in, which tends to be darker black and have a lower albedo. One way to think about this is that clear cuts are really hot. Essentially, you're replacing all of the highly reflective leaves with just bare ground. And you're going to get a situation where you have a lot lower evapotranspiration and in many cases lower albedo. As a consequence, your sensible heat flux is going to be a lot higher. And compared to an intact forest, clear cuts have a lot greater sensible heat flux and a lot higher temperatures. In addition to water and energy exchange, there are changes in carbon balance that occur over time with succession. In primary succession, productivity and heterotrophic respiration are often greatest in mid-succession. So if you think about you're starting with bare ground and you're going to take a look at over time as soils develop, where do we get the greatest peak in productivity and how long does that take? Does it have a situation where it does drop off, or does it stay relatively high for a long period of time? This graph here are successional changes in spruce production, this time in eastern Russia. And we can see changes in net primary productivity in the forest over time. So here's stand age on the x-axis, and it goes up to 160 years. And this is net primary productivity, grams per meter squared per year. This general pattern is associated with changes in the leaf area index, and we get the highest leaf area index and the greatest net primary productivity at intermediate age stands. Over time, for reasons having to do with nutrient cycling and other things, your leaf area index goes down and the primary productivity declines too. These general patterns can be idealized into looking at how different factors associated with ecosystem productivity change over time with primary succession. So just like before, we have stand age, and we're going to have a carbon pool or flex, and we can see that GPP, gross primary productivity, is highest at an intermediate age. Net primary productivity is also, but plant biomass is going to accumulate. This is generally for forests, and you can see that most of the successional examples we had were for forests, but plant biomass is going to accumulate. Plant mortality goes up over time, and that causes plant biomass to level off as there's replacement within the stand. But the highest leaf area and the highest productivity you get tend to be at intermediate stand ages. Here are some more idealized patterns of the changes in carbon pools and fluxes in primary and secondary succession. So these are things that I tried to draw out before. Here's primary succession and secondary succession. We've got stand age on the x-axis. Here's soil carbon and plant carbon. And over time, your soil carbon is going to go up as your soils develop with primary succession, and plant carbon is also going to go up because there's greater soil carbon, greater nutrient cycling, and that's going to generate greater productivity. As far as carbon fluxes are concerned, though, we still have intermediate peaks in productivity for something like NPP. With secondary succession, after the disturbance, soil carbon doesn't necessarily go down that much. And as a consequence, plant carbon can respond a lot faster. So you're going to have a situation where plant carbon is relatively low directly after the disturbance, but it can rebound relatively quickly. And we have the same general patterns of NPP and NEP being greatest during intermediate age stands.